Welcome to this video where I'm going to go through a concept referred to as absolute value. I'm going to introduce you to the concept of absolute value and what it means, what the notation and symbols are associated with it, and then we will examine the graphs of a linear absolute value function. Alright, so let's get started with absolute value and we'll look at a definition of it. And the definition of absolute value is how far it is from, on a number line, what is the distance from 0 to get to that particular point. So for example, if I say here, what's the absolute value of -4? Absolute value, is these two straight lines. Those are the symbols that mean absolute value. What this is asking is, how far would it be from the number -4 back to 0 on a number line? Well, the distance would be 4 units. This says, what's the absolute value of +4? How far is it from the number 4 on a number line back to 0? It would also be 4 units. So notice the absolute value of -4 and the absolute value of 4 are the exact same thing. Well, if we just quickly look at a couple of these, say, well, what's the absolute value of -10? It's 10, but the absolute value of -10 would be +10. The absolute value of 3 would be also 3. The absolute value of -4 would be +4. Now, a less mathematical definition of absolute value is that anything between these are called absolute bars. Anything that's found between these absolute value bars will just become a positive value. Or people will say, well, absolute value just means the answer is positive. And that's basically what it is. It's a way to make the value between the absolute value bars always be a positive value. Let's look at a few calculations here. So if I have, remember, these two straight lines imply absolute value. The absolute value of -12 would be 12 because it's 12 units from -12 back to 0. The absolute value of 0 is just 0. 3 take away pi. Now I'm just going to estimate this. So these absolute value bars, they act also like brackets. So this would essentially mean find the absolute value of 3 minus, I'm just going to approximate here and say 3.14, which would be -0.14, which would have an absolute value of +0.14. Again, treat bars like brackets. So do the computation between them first. -3 take away 5 is -8. Now once you've got it down to a single value, the absolute value of -8 is 8. -3 plus 5 would be 2. The absolute value of 2 is 2. One thing you'll want to try and do, I just thought of it when I wrote this down, if someone was to walk into this video and just kind of look right now, they'd say, oh, how come you wrote down 121? You may want to try and make your absolute value lines be a little bit taller than your actual numbers. Just that might be a bit too much, just so that you don't mix up 121 for the absolute value of 2. But that just comes down to your penmanship and how neat and tidy you can write. Alright, so this one would be -2 minus the absolute value of -3. The absolute value of -3 is +3, so -2 take away 3 is a -5. So you can see here one of the properties that you would have done with regular round brackets, you would say, oh, well, two negatives together becomes a positive. We cannot apply that principle when you have absolute value bars because you must make the positive value of what's between those bars first before you ever get to use that subtraction. Alright, so consider absolute value bars as if they were brackets. Absolute value of -1 is 1. Plus the absolute value of -4 is 4. 1 plus 4 is 5. -1 plus -4 is -5. The absolute value of -5 would be +5. Absolute value of -10 is 10. Absolute value of -7 is 7. 10 minus 7 is 3. Alright, so hopefully that shows you what this absolute value symbol means. If you weren't ever shown that before, now you should now at least have some context of the mathematical notion of absolute value. What we want to do now is move on to a more mathematical and graphing kind of aspect of absolute value. This would be a mathematical definition of absolute value. Now, if we just kind of try and examine this, this is what is referred to. We'll study these in more detail in grade 12, but it's called a piecewise function. And that is a function that does one thing in one area, and then it does something else in another area. Now, I want us to consider what this is saying. This is saying that if, so A is what is between these absolute value bars. It's saying if A is bigger than or equal to 0, that means if that's positive. So think of it this way. Imagine that between the bars was a 7. It's positive. Well, the answer to the absolute value of 7 is just 7. So it's saying if the number between here is positive, you can just write out the number without bars. You don't need them. The second piece of the function is saying this. Well, what if between the bars was a negative number? And I'm trying to write it here without absolute value bars. Well, the problem is if you say, well, just don't write out absolute value bars. You don't need them. Right? This is in between the bars is A. In between the bars is A. It's saying that if between those bars is a negative number, and you want to write it without absolute value bars, well, you're going to have to take the negative of it, because a negative of a negative will turn it into a positive. And we know that the absolute value of negative 3 is supposed to be positive 3. So down here just kind of shows you, if you have the number 5, the absolute value of 5. Well, 5 is a number that's more than 0, so your answer is just 5. This time, notice my answer is negative 4 over 7. So I know we simply say, oh, well, you just make it positive, which is really what you do, but how do you make a negative become positive? By taking the negative of it. So a negative times a negative, hey, look at that. There's our positive 4 sevenths. Now you don't have to worry about it if it's 0. So if we look at, let's suppose the absolute value of x minus 2 instead. And I say, well, what would that be as a piecewise function? I like to kind of use 2b, bp, which stands for between the bars, these bars, is positive. Well, the first thing you say, well, how would I get between the bars positive? Well, between the bars, write out what's between the bars. X minus 2. And I want that to be bigger than, or I'll also let it be equal to 0. Well, that's only going to, so now you're going to solve this. I'm going to move the 2 over. That will only happen if you put a number in there that's greater than or equal to 2, which makes sense. Think about this. If I put 5 or 7 or 10, anything more than 2, I will get a positive number in here. Well, if between the bars is positive, we said that you really don't need the bars. They don't do anything. So this, let me put a y equals in front of this. I forgot that. So there's where between the bars is positive. The other option would be B, B, N, which I'm going to use as an acronym for between, oops, sorry about that, between the bars is negative. You say, well, how's that going to happen? Well, I'm going to write out what's between the bars, x subtract 2, and I'm going to say that can only be negative if I put a number in there that's less than 2. And that, again, should make sense. If I put 1 or 0 or negative 10, and I subtract 2 from any of those numbers, anything less than 2, and put it in here, you're going to get a negative value between here. Now, if we go back to what it said up above. So here's what I mean by a piecewise function. So I'm basically trying to write this function. Right up here, I start it with absolute value of, they just use A as a generic start. Well, I'm saying that if I go y equals, there are 2 possibilities. It will just stay the way it is if it's already positive. Well, it's only going to already be positive if I put a number in for x that's bigger than or equal to 2. And then it will say, well, it'll switch to negative. So if this was a negative, we know that it's going to switch to a positive. So it's going to be the negative of what's between the bars if the x value is smaller than 2. That's how you write an absolute value function as a piecewise function that doesn't have the absolute value bars on it. Alright, let's have a look at another one of those. So let's suppose that I've got y equals absolute value of 2x plus 3. And I want to write this as a piecewise described function that does not use absolute value bars. So remember, there's two scenarios you got to be concerned with. What if between the bars is positive? So remember, if between the bars is positive, that means 2x plus 3, there's between the bars, must be bigger than or equal to 0. That means positive. You're going to determine what x values will make this happen. So 2x is greater than or equal to negative 3. X would have to be greater than or equal to negative 3 over 2. If it does, then you do not need the bar, because you don't need the bars. It's already a positive value. Again, make the analogy of numbers. If you had the absolute value of 3, which is already a positive number, I really don't need the bars. They don't do anything. And then you have this scenario. Between the bars is negative. Well, we need to determine what will make that happen. 2x plus 3 could be less than 0. That would only happen if 2x was less than negative 3. So x would have to be less than negative 3 over 2. And if that's the case, you must take the negative of what's between the bars. Because we know that if it's negative, you need to take the negative of it because it's supposed to come out to be positive. What, you say that sounds confusing. This is what it means. If you have negative 3, and I want to write that without absolute value bars, between there is already a negative number. Well, if I just say, okay, I won't write absolute value bars on it, well, that's not correct, because the absolute value of negative 3 we know is 3. So if it's negative, I need to take the negative of it. Negative, negative would make it positive 3 the way it's supposed to be. So if between the bars is negative, we must take the negative of what's in between there. And now we just kind of put this all together in a nice, what we refer to as a piecewise function. So it will act like this, 2x plus 3, if the x values are bigger than or equal to negative 3 halves, and it will act like this, negative 2x plus 3, if the x values are smaller than negative 3 halves. Alright, so that's the first thing we want to be able to do, is write a piecewise described function, write an absolute value function as a piecewise described function that doesn't have absolute value bars on it. Okay, let's move on to what the graphs of absolute value functions look like. So if I start with, this is what we would call our base function. Our base function for absolute value is y equals the absolute value of x. So we're just going to put these x values in here and spit out the y values. So absolute value of negative 3, 3. Absolute value of negative 2, 2. Absolute value of negative 1 is 1. 0. Now these ones are already positive, so the absolute value of already positive numbers, they would just stay the way they are. So 1, 2, and 3. So I've got 0, 0, negative 3 and 3, so negative 3 and 3 would be roughly there. Negative 2 and 2 would be there. Negative 1 and 1 would be there. 1 and 1, 2 and 2, 3 and 3. Well, I think we've got enough points to see that I'm going to get a line going this way. I'm going to get a line going this way. So there's what we now know about absolute value. Now this only is true if it's a linear, so an x to the first power between those bars. We're going to get what we refer to as a V-shaped graph. Now we're going to look at some of the different properties of these graphs. In terms of, it'll have something that's referred to as, just like, it's very, very similar to quadratics and what we've already studied with quadratics. So you'll see lots of similarities here. So this is referred to as the vertex. It will also have a stretch factor. So This one you can see it goes over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1. The nice thing about absolute value as opposed to quadratics, if you go over 1 and up 1, well, the next one, if you go over 2, you had to go up 4 because you were squaring it. These ones, that's not the case. It's going to be over 1, up 1, over 1, up 1, over 1, up 1 in both directions. Well, if we look at the line y equals 3x plus 4, so imagine I just asked you from your knowledge of straight lines, I said draw a graph of 3x plus 4. Well, this is already in mx plus b, so I know it has a slope of 3 and a y-intercept of 4. So I'm going to put the y-intercept on here at 4. The slope of this line is 3, which means rise 3. So rise 3 and run 1. Rise over run. I could also go down 3. So I'm at 4, down 3 and over 1. That would give me another dot. And then I would have, this would be the graph of y equals 3x plus 4. Now, based on your limited knowledge that you've acquired over the course of the first part of this video, I would now ask you to say, well, what do you think would happen if I wanted you to graph the absolute value of 3x plus 4 instead? Oh, let's not put that on there. So let's use a different color and say, well, what if it was this instead? What we do know is that if you take the absolute value, it should make all of these numbers, all your y values, the answers here should always be positive. I should never get negatives. Well, on this part of the line up here, the y values are already positive. Nothing should happen to those. But then when you start down here, when you take the absolute value of this number, which let's say it's at -1, it should jump up and switch to +1. This one, which is here, should switch up to +2. This one that's here, which is at -4, should go straight up to 4. And your graph, so in red, right, nothing happened to the positive numbers because they were already positive. But the negative, these were negative y values. The absolute value of those negatives switched them to their corresponding positive. And that gave my graph, as we saw in our base function, it gave it that nice V shape again. So this had a V shape to it again as well. Now, let's look at, I'm going to just switch here for a moment to, wrong thing. I'm going to switch to Desmos. We're just going to look at some graphs and see if we can come up with some properties here and see if you notice any similarities. So just so you can watch for a minute or two here. Let's start with y equals. So if you're in Desmos, if you type in ABS, it interprets that to mean absolute value. Put your bracket. There's your absolute value of x graph. Now I'm going to, on the same, so I'm going to leave that there so we can use it as our kind of reference. That's our base graph. Let's look at what happens if I put in here y equals twice the absolute value of x. Now think of your knowledge of, and I haven't finished typing it yet because I want you to think first, the similarities I said there's going to be between this and quadratics. So think of y equals x squared as your base, and what would happen when we put a 2 in front of the x squared? Well, let's see if the same thing happens here if you're trying to remember. So 2 absolute value of x will show up in blue. So you can look at the color scheme, it's in blue. And you may say, well, what happened to it? And you may say, hey, it got narrower. And it absolutely did get narrower. And the reason it got narrower is because this one originally had a 1 in front of it, which we talked about that being our stretch factor, we called it, when we did quadratics. And that meant if you went 1 to the right of the vertex, it would go up that number, 1. This is now, if you go 1 to the right of the vertex, 1 to the right of the vertex, notice instead of going up 1, it's now going to go up 2. So it's going to go up 2. And what that does is it makes the graph appear that it's getting narrower. It makes the V narrower. So if I was asking, so well, how can I make the graph even narrower than the blue one? Someone might say, well, why don't you put a bigger number in front? And we'll try that. Let's make it y equals, 5 absolute value of x. And the green graph here, which you can see, it got even narrower again, and the reason is I went over 1. This time the stretch factor is 5. That means if you go over 1, you should be going up 5 units, which is what I did right to there. Left 1, up, look where I hit the graph. It gives you the coordinates. Whoops, didn't hit it. There you go, -1 and 5. And that has the visual effect of making the graph, the V, open narrower. Well, one might say, how would I make those open wider? Again, same as quadratics. Instead of putting a number more than 1 in front, you would simply put a fraction there. So something like 1/3 of the absolute value of x. And what happens now is, when I go over 1, like I was before, over 1, now I'm only going up 1/3 of what I used to, which originally was 1. So that has the effect of making the graph, or the V shape in this case, open wider. Alright, so that's a number out in front controls the width of the opening of our V shape. How do you think we could make that V open down instead of up? Now, sometimes students get confused here and say, well, that's impossible because absolute value is always positive. And it is, but that's only between the absolute value bars. If I was to take and write out the function y equals and put a negative not inside the absolute value but out in front, look what happens. That essentially, because this absolute value of x is always positive, but then I'm going to take the negative of my answer, that's going to guarantee that my y values are always negative, which means the graph's going to open in the V shape still, but it will open down instead of up. Alright, so that's how you determine whether your absolute value graph opens down or up. You look out in front of the absolute value function and whether that's a negative or a positive. The number that's out in front will determine how wide the V shape is going to open. Well, let's think about now, what if I put inside this bracket a +4? I want you to look at what happened. It made our V shape move 4 units to the left. So it moved the vertex 4 left. Now, based on your knowledge of quadratics, would you say that's exactly what you would have had happen if this had been x plus 4 squared? And hopefully you'd say yes, because that would give you a vertex of -4, which moves it over to -4. If you want it to go right, let's say 5 units, all you need to do is switch that +4 to a minus whatever, 5 would go 5 right. If I want it to flip over and say, I don't want it opening down, I want it to open up, there you go. Say, oh, I'd like that to be a little narrower. Okay, no problem. There, made it narrower by putting a 3 there. So I'm starting to kind of get a sense of what happens when I put numbers in certain locations, and that's kind of what we're trying to get out of this. Then I may say, okay, well, no, let's get it back to the width of the same width as the other one. There you go. I really like to move that vertex down 4. So then outside your bracket, put a -4. There you go. So now the V has its vertex at +5, -4, which is, as I said, the same as what would have happened with a quadratic. Now, if I want to have a whole bunch of changes, I could make it flip over, put a negative, make it narrower, or let's make it wider. Let's put a fraction there. Let's put 2/5. Oops. Get up there, why won't that work? Okay, to put a fraction in, you use the divide sign on your keyboard. So it would be -2, or I guess it's just a slash, like the sideways. There you go, -2 over 5. That should make it wider. Absolute value, let's suppose I wanted it to go left. So I'd put, I don't know, plus maybe 2. That should go +2. That moved it left 2. And I wanted it to go above the axis, so instead of -4, let's make it go up 3 by putting a +3. So you can see that by me typing in these numbers, I already knew in advance what was going to happen. And that's what we'd like you to have the sense of. When people put numbers in certain places, an absolute value linear function, so it's got to be an x. Now, as soon as you put an x squared or an x cubed or something in here, everything we're talking about goes out the window. This is only true for linear absolute value functions. Okay, so let's try and summarize what we just talked about here on this page. In words, let's look at, so without using graphing technology, this is our base function. Let's look at these and say what should happen. So this should move left 2. This should go right 3. This one should go left 2 and down 3. This one should go left 2 and up 1. This one should go left 2, up 1, and the 3 will make it narrower. And when it says left 1, up 2, and they say, well, what are you talking about? Which graph are you moving? We're always referring to what would happen to the base graph, and this is the one called the base graph. So this graph would be narrower than the base graph. This would move the base graph left. This would move the base graph up, down, whatever. So if we summarize that with letters here instead of numbers, and I was to say, all right, the shape of this graph, these are just some properties. I think we can all agree now that it's V-shaped, again, as long as it's x to the first power in between the absolute value bars. Where would the vertex of the V have to end up? It's very similar to quadratics. It would be at h. So if that's a minus h, it's positive h. And this one stays the same, h comma k. Which direction does it open? That's controlled by the a. If a is less than 0, that means negative. It opens down. And if the a value, the number out in front, is positive, then it will open up. The axis of symmetry, so just like a quadratic, has a line that cuts it in half, which is always x equals the x-coordinate of your vertex. These are the exact same. If you draw a vertical line through the vertex, which is always going to have the x-coordinate of h, x equals h will always give you your axis of symmetry. We will assume that these graphs have arrows, unless we're told otherwise. So the domain, this graph goes forever this way, so it's eventually going to cross all the x's. It goes forever this way, so it's going to cross all of the x's on the negative side. So x could be any number. Now the range is twofold. You got to look at two things. You got to look at whether it opens up or down, and then you look at the y-coordinate of your vertex. So it's either all the y values are bigger than or equal to k, if it opens up, or it will be all the y values are smaller than or equal to the y value at the vertex if the V shape opens down. Now let's put all this to work and see if we can. This is typically how I would ask this on a summative assessment. I'd get you to fill in this chart. So I'd say, all right, here's a function. It's linear. Complete the chart shown below. Shape of the graph. So it is a V shape. Make sure your V looks like a V and not a U, because it could be misinterpreted for you to think that it's a parabola. Which direction does it open? Look right here, and I would say down. Where's the vertex? The vertex is at -3 and +4. Where is the axis of symmetry? X equals -3. Where's the domain, or what is the domain? The domain would be x can be any real numbers. Now this one, there's your vertex, and it opens down. So all the y values should be lower than the y value at the vertex. So all the y values should be smaller than or equal to 4. These are actually very easy to sketch. All you use is the vertex and the stretch factor. So the vertex is at -3 and 4. -1, -2, -3, 1, 2, 3, 4. You put the vertex, so -3 and 4. And then you're going to use 2 more points. So in this case, the stretch factor, and this is the same way we did quadratics, is a 2, and it opens down. That means from the vertex, if I go 1 unit to the right, this is -3, This is 4. 1 unit to the right, it should drop down 3 on your scale. Over 1, down 3. That'll put me at 1. Well, then if you go 1 this way, the same thing should happen. 1 this way, down 3. I missed. Try and draw that through there. Straight lines. Don't make curved lines. I'm doing these freehand on a stylus thing, so it's not as easy as it may be with a pencil and paper, but it should roughly look like that. So you can see I went over 1, down 3, my stretch factor. And I had my vertex here, -3 and 4. So hopefully you can see a lot of similarities between this and quadratics. The only thing different is the shape of our base graph. It's a V shape rather than that U shape of a parabola. Alright, that's it for our properties of absolute value functions up to this point. Hopefully that gives you some insight now into a new concept for many of you, absolute value. And we've led up to at least some basics in terms of the shapes of the graphs, how to move them left, right, etc., etc. So now you can complete some practice, do a summative assessment that will, or sorry, not a summative, a formative assessment will follow on this material, and hopefully that'll get you ready for the continuation of this, which will now build upon this information. Thanks for watching, and best of luck.